There are key methodological things that we need to think about. So this is very much the study of methods at this point. So the first thing really comes to terminology. And there is a huge amount of terminology that exists. I'm not really going to dwell into these, but you can see there is so much going on here where to define what is called a first threshold and a secondary threshold. And a lot of the terminology seems to overlap. You can see, for example, that we've got onset of blood lactate accumulation. We've got, for example, ventilatory thresholds and ventilatory breakpoints over here. We've got a second ventilatory threshold and so on. There's all sorts of things going on. The key thing to understand is, and this is where this gets incredibly confusing, is that there is an awful lot of what I would call chatter within exercise physiology. And most of it is, I think, to a certain degree, quite confused. And the confusion is really showing here, because oddly, what the authors have got here is this point here. This is where it gets really confusing. They've defined this as the first threshold. So they're saying the first threshold. What do they mean by the first threshold? Well, they actually mean this point here. Gosh, that's confusing, right? Because this is the transition from, remember, from moderate steady state exercise to heavy non-steady state, and then severe, which is absolutely non-steady state exercise. And so therefore there has to be a demarcation between heavy and severe. So the demarcation between heavy and severe is what they're terming the second threshold. God, that is really confusing. For the currency of this session, we are going to refer to this point as LT2 as a second threshold, and this is the first threshold. If you want to know, I'm going to use this as a marker point here, what this point here is, which is fundamentally the transition from heavy to severe, then do go and join the class which is on gas exchange thresholds, and also, as I say, the class in related to oxygen uptake kinetics. So it's really confusing. It gets even more confusing because, as you're about to see, they have thrown in here under the second threshold, which is higher than what we're terming LT2, things like onset of blood lactate accumulation, individual anaerobic threshold, and so on. And yet, as I'm about to demonstrate, if we were using their definitions, they would actually fit under the first threshold response. So it's absolutely littered with issues and mistakes. So how do I advise that you should really define these points? This point here, which we're calling LT2, really you should call it the lactate turn point, because it's an easy way of thinking about what's going on. What's the lactate doing? It's turning away from linearity. So it's a really easy point to define. The lactate is turning, LT2. So what should we call this point? Well, it's a little bit more complicated, I suppose, coming up with an alternate term. LT1, we tend to call it the lactate threshold, which does understandably become quite confusing. But LT1 is a simple way perhaps to abbreviate it. So to reiterate, LT1, LT2. Okay. Lactate turn point, it's turning away from linearity. Lactate threshold, really where we start to see this first initial appearance of blood lactate. But for the rest of this class, we're dealing with this point here. So let's think about the methods, which are perhaps a little bit easier to understand than even the definition, thank goodness. So the first thing is, let's think about, for example, the basic things to think about. So this is a paper that was written a while ago now, but it's actually really useful. It's in sports medicine, and it gives us some really nice information. From a methodological point of view, the site, that is the earlobe or the fingertip, as well as the method, is it venous, arterial or capillary, of blood sampling, and the laboratory methods, that's the lactate analyzer, the analyzed blood medium, may also affect the test results. Samples taken from the earlobe have uniformly been shown to result in lower blood lactate than samples taken from the fingertip. In addition, several studies reported partly considerable differences between various lactate analyzers, portable field versus laboratory analyzers, photometric methods, and under various climatic conditions. So there's an awful lot of things that seem to affect the response. So the first thing is to remember this. There's a difference between internal and external reliability. Internal is what you're doing within your own laboratory or within your own test environment. So if, for example, you only have access to a handheld field-based lactate analyzer, something like a Lactate Pro or a Lactate Scout, then you just want to ensure that you've got consistency within your own laboratory. So on a test-retest basis, you should get consistency within your laboratory. It only becomes problematic if you're comparing to a device from another laboratory. So that's the first thing. So as long as you use the same device each time and you've checked it for reliability, that is absolutely fine, because you should still be able to see the responses. The second thing then is kind of the validity of those analyzers. Well, that's a different question. Some of the analyzers, which we'll get to later in this session, do give, unfortunately, odd results, which will explain why some of these may be odd. The second important thing then is where do you take this from? Where do you take the analyzer, the sample from? Well, conventionally, most people will talk about taking the sample from the fingertip because it's convenient. It's very easy to get the sample. If you're doing the sampling, there are all sorts of different schools of thought on this. My approach has always been to get the sample taken from the pad of the finger, not on the side, not on the tip, on the pad. It's got a high capillary density, so it's going to bleed quite well. The second thing is for the milking of the sample, and we don't want to over milk the sample, but we want to milk it a little bit to kind of start to get a little bit of flow. I've got much more control if the blood is going to pool on the pad than it is on the tip of the finger or on the edge of the finger, because I've got a bigger surface area. I've got greater control. Once I've got greater control, it's much easier then to get an accurate collection. But then you've got this issue of, okay, if I'm not taking it from the finger, which you may not do, where else could I take it from? As the authors have said, well, you get differences from the finger compared to, say, from the earlobe. Well, conventionally in swimming, we do take it from the earlobe, because the swimmers will come into the pool side, we'll be on pool deck, and quite often we may not even get the swimmer out of the water, so it's easy to lean over and take it from the earlobe. In rowers, conventionally what we will do is we will sit at the end of the rowing erg, they'll row with shoes off, and we'll take it from the big toe. The reason for doing that is a health and safety thing, and that's the same that we would apply with cycling, that we don't want to get transference of blood onto the handle of the rowing erg or the handlebars of the cycle ergometer. So to a certain degree you have to kind of balance practicality with health and safety. So let's move forward a little bit. So this is from a paper from Keir and colleagues published in 2002. And they write this: because blood lactate and VO2 take time to stabilize during exercise, their relationship within an individual can be influenced by step duration and number of steps. So we're now thinking about protocol. So in previous classes, we've talked about how we might assess something like VO2 max. We've talked about step duration, step increment. Longer steps, e.g. 10 minutes, are likely to provide a more accurate representation of the blood lactate associated with a given VO2. But to maintain reasonable test durations, fewer steps are performed, typically with greater work rate amplitudes, which reduces the precision of the lactate turn point and lactate threshold identification. So let's think about what they're arguing. They're arguing, which is absolutely correct, that if you have somebody running or exercising for a longer period of time, you're going to more likely to get a more representative response of the blood lactate profile. And this is absolutely true both in the moderate domain, that's below LT2, and also in the heavy domain, which is between LT2 and a point that we've not talked about at all in this class, and we won't talk about until we get to the gas exchange threshold class, which is what we call respiratory compensation point, or maximal lactate steady state, or critical speed. They're all one of the same point ideally. And what we know, if we're working in the heavy domain, it actually takes between 6 to 8 minutes for lactate to stabilise, as with the VO2. So it kind of lends itself to having longer stage durations in order to compensate for the fact the lactate will still be rising. But in order to prevent the test becoming too long, I mean, if you imagine that you started somebody at 11 kilometres an hour and you were doing 10-minute stages, and they're going to go up to 17, 18 kilometres an hour, they're going to be running for close to, what's that? I mean, 10 minutes per each stage. They're going to be running for, that's 8 stages. It's an hour and 20, hour and 40 minutes. It's way, way too long. And, you're never going to get an athlete to commit to it. So the compromise is that you reduce the stage duration to increase the fidelity in the data by reducing the increment step, so the size of the step. So typically what is done are 3-minute stages and smaller increments. So that might be a 1 kilometre hour increment on a treadmill, or if you're working with a cyclist, it might be something in the region of 2 watts per kilogram increases, or something like 25 watts increase. So it's, again, a little bit of a compromise. Are there ways around this? Well, yeah, I mean, if you have worked with an athlete before and you know roughly where the transition is between moderate and heavy intensity exercise, you can start to just throw in those longer stages for that little section that you're working on. Or if you're trying to think, well, I want to be precise in the fidelity of the data, reduce the duration, reduce the size of the increments. So rather than doing, say, 1 kilometre an hour, go up by half a kilometre an hour. So there are compromises that one can make in order to be able to fundamentally produce a protocol that suits the needs of the athlete.